Hi, welcome. I'm Nicholas Carell. We'll be talking about robots getting a grip on general manipulation. I'm a professor at the University of Colorado and the founder of Robotic Materials, Inc. I really enjoy working both in industry and academia to see what we really need to do to get general manipulation out there. Let's look back where we are at in robotics. Probably the biggest deal has been autonomous driving. It started really with the DARPA Grand Challenge in 2005. And winning that has showed industry and the general public that it could be done. And so a lot of money was spent to get the first commercial ride in February 2020 by Waymo and many other startups who are now delivering food and medication on the streets and sidewalks. Manipulation, we are not quite as far. There has also been a DARPA Grand Challenge on humanoids, where the focus was on remote control. At IROS, we enjoy the grasping and manipulation competition for the last 4 years, thanks to Professor Yu Sun from University of Florida, who is putting a lot of effort into organizing this and having many stakeholders bring out their challenges to test where we are at the community. Here you see basic household manipulation tasks, but there also is an assembly track in collaboration with NIST. There is a big assembly competition in Japan every year now, the World Robot Summit. The Amazon Picking Challenge has created a lot of excitement because of the strong commercial potential that this application has. And indeed, we have seen a couple of companies that are now successfully selling picking solutions based on suction. The manipulation market is quite interesting because everything is already quite automated. If you think about, let's say, for example, a light bulb that goes off in your house, there is a system that would probably know that already. It could order this thing automatically and trigger this entire process of the raw materials being brought to a factory and then eventually shipped into a storage facility. And once you need your light bulb brought to your house, where they have to be plugged in, and the old one has to be recycled. Now, all of this is quite automated or could be automated except for the manipulation aspects of it. So we have companies that are working on that specifically. Since the 80s, we really have industrial assembly, welding and things like this, and it's all very well known. And more recently, we have a new breed of robots that are doing things more autonomously. And here I try to put up a couple of companies right underneath where they are in that chain of consumption. And so now you see there's even robots that can feed people. There are robots that can pick things out of shelves and create a order, fulfill an order. There's AMP Robotics here in Colorado that does recycling. But what these robots are still not do is they're still not really competing with humans when it comes to general manipulation. They are still machines that are purpose-built for their specific application. So I think what the challenge for us as a research community is to really get there, unearth that potential, because then you would have a robotic solution that could do all these things much like a human can. So to understand what manipulation is, most people think about grasping as the problem of finding where to place fingers onto an object, so to get a constraint and or constrain it and not let it have slip. The actual real challenge is to put these constraints at the object on at the same time. So if you think about the screw standing on a tabletop here, we all know how to grasp it with 2 fingers, but if you would close your gripper now, the screw would fall, or worse, it would actually spin out of the gripper and leave the table. So in order to solve that problem, you have 2 options. So either you increase perception accuracy, so you make sure you really know exactly where that screw is, and you position your hand accordingly. You know, if you're lucky and you close your fingers, you will just reach the screw from both sides at the same time. The alternative or complementary thing you can do is you can use compliance. And in this case, the fingers are kind of spring-loaded. That's the best way to imagine it. and they just keep closing until they hit, but limit the force with which they do so. So if you have very, very sensitive force control, you could imagine to grasp that screw with 2 fingers without it falling or slipping. So in order to address that, these challenges, we developed a tactile sensor that can do both increase perception accuracy and measure force. So here it is. You see, we press it down, and I label these things with SA1 and FA1, like akin to the human tactile sensing system. Now, what you see in the FA1 signal, you see the actual touch event. So there's a touch and release event, and let me play this again. Whenever the device gets touched, I get these peaks in the FA1 channel. At the same time, I see in the proximity as the strawberry approaches in this case. So we were quite excited about this. Here's how it works. It's an infrared proximity sensor that is integrated into a flexible and transparent polymer of known width. So the idea is now that if I shoot the infrared out, I can get it reflected from an object and measure the distance to it. But I can also measure the deflection of the material when I exert some force. And so this is simply a Hooke's law. F equals spring constant times the displacement, which I can measure and from which I can then infer the force. So here's how that looks like. As I approach my sensor, I get some increasing sensor value. And then there's this point where I touch the object, where I turn it from a proximity measurement into a pressure measurement. And likewise, I can tell once I release the object that the sensor value now should be treated as a proximity value again. So if you think about that in the context of grasping, you can think about using such a sensor to correct your approach and first align with the object, so to not disturb it too much. Then you can detect the contact event, you can detect loading events, disturbances like wrenching or tapping it, and finally even replacing when you place the object back on the table, after which you would release it. So we used this in the IROS competition, I think in 2016, and made fingers for the Canova hand. And here the idea is that this spoon would actually spin out of control if you would touch it too forcefully with your fingers. And also it is hardly visible in the ASUS Xgen 3D data feed. And so the idea is that we can use those sensors to actually find it and then manipulate it gently, which works very well, as you can see here. Now the gripper grasps the spoon, and it will then do some scooping, where we can again use the sensor to detect the event of hitting those beans. So we got quite thrilled about all of this and thought, well, we finally solved manipulation, and we need to start a company to bring it to everyone. And so what we did is we started selling that sensor, and for the Baxter robot and the Robotique gripper and the Canova fingers, and many of you have bought one, and we're very grateful for that because it really moved us forward. But it's also a difficult business to be in to make sensors. So we started the company to do more industrial manipulation things and raised $100,000 from the state of Colorado to the university, allowing us to buy a universal robot arm and then exchange a license with equity with the company. So this is the product we came up with. This is an industrial assembly scenario, which is based on the IROS Manipulation Challenge assembly task. And what we've done is we created a UR cap, which is a plugin for the universal robot, allowing users to use this sensor information in a meaningful way and, for example, detect something laying on the table or detecting contact events. So what we've done is then we programmed this assembly task, and we hard-coded it into the universal robot, and I show now what the sensor would actually see, which with the reasonable thresholds you can then use to control your process. So here are these touch and release events as I go and grasp and re-grasp the device. Now, the problem with this is the market is relatively small. It's people who own a universal robot and a robotic gripper and actually want to do these kind of assembly jobs for other people. There's another problem. If such a transaction takes place, then a lot of people make a lot of money, except us who sell the sensor. So we then went to the NSF, which has an SBIR program, which I can highly recommend to all of you who want to transition your technology, and received $225,000 to create a hand, which we thought will then allow to capture not only the sensors market share, but also the cost of the gripper and even a vision system. So we then hired the first engineer, Austin Miller, fantastic guy, and he built this hand from scratch, designed it, and I would describe it as an iron hand, articulated two-finger hand, which has two motors to drive each of the fingers individually, an Intel RealSense stereo camera, and an NVIDIA Jetson that does most of the control and processing of the information. There's a patent that we submitted which describes the hand in great detail if you're interested in how it works. I show you some demos of what it can do. So the first video we released was a mobile manipulation demo using the Canvas card. Canvas Technology was a company in Boulder. It's now Amazon Robotics, and it allowed us to demonstrate approaching a bin without docking, without knowing exactly where the card is, but for like 10 centimeter accuracy. Then using the onboard camera and processing to detect those screws and grasp them. So we usually try to make videos where we show a sequence of actions, because then it is clearer that this really actually works, not only once but many times. Now it grasps a belt from the World Robot Summit assembly competition. It then drives the card elsewhere in our shop and will drop the bin there. Let's see, let's fast forward that a little, because this is just driving. Now it will again use the onboard sensors to look where the bin actually is, and then grasp it and place it. So with that you can create some quite reliable, robust real-world kitting tasks. And I will explain you a little more how it actually does that. So the first thing is, iron hand is really the key to minimize calibration error. Whenever you have the camera elsewhere, you will have centimeters, up to centimeters of error, because it's just impossible to calibrate the camera the same way everywhere in your environment. Now, when you look at the stuff like this from above, you can approach it up to 12 centimeters. There's a dead zone, but then get a depth measurement, segment and filter the point cloud information, compute the principal axis of the point cloud, do collision check to select the best grasp, and then grasp. So here's another video on how this works. This is a bin picking application. We use fake fruit because for obvious reasons we can't keep them around for too long. I mention it because they're actually much more slippery than real fruit and also more reflecting. This works again quite well. The robot approaches the bin, looks inside, and does what I just described to select the best grasp. There are a couple of error cases that occasionally happen with this kind of setup. Let me fast forward. Sometimes you might not find an object. You might need to scan the environment. Here it slips, which is due to the slippery objects. but then it will look again and actually grasp it. So here is an example where we use some real fruits. These are strawberries. Generally, there's this belief that you need soft actuators to do fragile objects. That is not the case. It is sufficient to control the force. And so you see how I can grasp all these strawberries and not crush them. So to give you an illustration on how this works, the key is very simple impedance control, which we achieve by simply controlling the current of the digital servo motors. And so in this case, the torque that you get is proportional to the maximum current you set. If you set that current to be very low, you can deal with situations like this where the gripper gets stuck at an obstacle that you might have not seen. Any normal gripper would now not be able to close anymore. Our gripper will just stop one finger and keep closing the other. And again, the torque is controlled in such a way that the strawberry wouldn't be squished. So another example of what the hand can do is another mobile manipulation task. This time we have received the phase 2 of our NSF SBIR grant, which allowed us to buy a Mir card, which works very well, and demonstrate a restocking task. So for restocking, what you need to do is you have to check what needs to be restocked, then take out the original items and put in the new ones, and then put the old bottle in front so that the next customer will take that one. So this is what happens here. This is all autonomous. We just assume that we know how the robot has to move in order to insert a bottle. So this motion is a pre-programmed motion that we associate with bottles. So we know that we can grasp them at the top and then make that motion, which allows them to pivot. Everything else is autonomous. It looks where things have to be placed every time. It looks where the bottles are in order to grasp them correctly. And so again, in order to show that this actually works more than once or is actually autonomous, I think the only way really is to show you sequences like this. So I think it will do one more bottle and then replace the old one, which you saw it placed itself. So again, it has to look first where it actually is. Also, this motion is of course pre-programmed. We know that we can push bottles back and create space that way. It's a behavior that is associated with that object. So now it will look again. It adjusted a little bit its pose to grasp and puts in the final bottle. So what is new here, or how to do that? The idea is to integrate 2D and 3D perception to do semantic reasoning. So with the RealSense, we not only get the depth point cloud that you've seen, we also get RGB images, which we can then use, in this case, with orb features, but you can also use mask RCNN, which allows you to get semantic labels of what objects are. And now the cool thing is you can use those semantic labels to label your point cloud to know which points are actually belonging to the Soylent bottle and which one are Coke and so on. And so then I can use the grasping algorithms that I showed you earlier to just focus on that point cloud. Another case study that we are very excited about is industrial assembly. This is the World Robot Summit Industrial Assembly Task Board. The way assembly in industry often works is you are given a kit. Kits are brought to stations. This is a kitting mat in this example. You can also have a kitting tray, which you see here in the background. And part of the competition was to do to populate those kitting trays from those bins. There's some videos on the website if you're interested in this. But essentially, we are picking all these parts that you see here from these bins to create that kit. And now we use force-based insertion to insert these items. And let's wait for, this is one more peg and hole, but let's wait for the belt assembly. It just checked where these pulleys are. Now it uses a behavior that we pre-described to actually add the pulley. Again, it uses force measurements to test whether it works. Also, that works very robust, so we can do this over and over again. You can also join us at the IROS assembly competition this year, where we assemble a slightly different task board. So in order to do this, you need one more thing, which is a force torque sensor. This is a 60 OF sensor that measures the forces and the torques at the wrist. And once I have such a thing, I can define behaviors like move down until touch and gently touch the surface of the table or the assembly plate. I can then execute something like a spiral search, where you see the forces here, and you see the spiral force, the spiral motion in the force measurements. And once I actually find the hole, the z-force goes back to 0, which allows me to insert the object. If you're interested to learn more, we have a journal paper that just came out on the WRS challenge and the algorithms we use there. Now the question though for me is that also guided my talk: is this general enough for business? Are we already there that industry can actually adopt these things? And if not, what it is that we need to do? And so we made a couple of observations at the competitions, trying to sell these things and writing papers about them. And so the first one is really general solutions are very expensive and slow, and specific solutions are always better. So if you're at a competition and you're competing with somebody who made a machine to just insert those specific objects, then that solution will be probably better. The other thing is general solutions are difficult to configure. So robots need to be truly intelligent so that you can work with them. If you think about the restocking task, I can imagine to tell the robot where these bottles are and where to pick them, but very small aberrations will throw it up, and a human worker would probably just look in the vicinity of the location that they were given. A robot can not do that, so we need to really also up the general intelligence in order to get to general manipulation. The second observation we made is return of investment, ROI, only works on a subset of customers. I asked my LinkedIn followers how much they would pay per month to save $200 in gas. Hyper-rational answer is $200 because you save the environment and you save a trip to the gas station. Many people, though, actually are not willing to pay more than $50. And the majority, a slight majority, believes in some kind of fairness in that they are not ready to give someone else the lion's share of their savings. So if you want to replace a task that you pay $2,000 in labor for, then you might not be willing to pay more than $1,000 to that company. So I think the problem here is robots need to really be super cheap, or you actually have to completely lose that angle of trying to replace workers and directly compete with a human salary. So in our company, we have a hypothesis that we can maximize efficiency and throughput for manufacturers by using robots for process analytics and control. So instead of having a robot replace a human worker, the robot actually does some bookkeeping and things that help with the process that a human wouldn't be able to do. So the approach is to look back at all the technology we developed over the last years and really break it into these different components that can help us to do that. And first, to start with deploying intelligence into the manufacturing line using simple vision products. Then use autonomous mobility to help move products, and only then at the very end use autonomous manipulation to complete the automation cycle. And to give you some examples here, what vision could do, already you could take inventory of things, look into bins, estimate the volume of what is in there. You can track your floor space And in manufacturing, that's very important because every inventory you have anywhere or stuff that builds up somewhere is waste. And you can also find resources like empty carts or pallets of things like that. The other thing is with vision and the 3D vision that we developed in this manipulation context, you can understand activity. So in this case, this is a packing task, and the question is the box open, yes or no? And this is our accuracy to do that. So even if people put in dunnage, we can still see that the box is still being packed, and once it's closed, we know it's done, and we can get a cart to fetch it, or we can bring the next box or print a label or something like this. The other thing is another example of how robots can help is to trade throughput and mobility. And for this, I have a little animation here. This is a typical manufacturing process which has some takt time and some transportation time. And so this object needs to be changing colors on these 3 different stations. Now there are 2 different ways of doing that. One is the job shop and the other is the flow shop. In the job shop, you do an entire batch, then you move it. In the flow shop, you pass on the object immediately. And now, of course, you're trading throughput with mobility. So even though a flow shop is much faster than a job shop, you actually need to move much more of the materials. And this only becomes attractive if a robot does it. Also, you would need to work in parallel, which is something that you could more easily do if some of these stations would be manned by robots and not people. So what's next? I think what we are seeing is that combining sensing, actuation, and planning can really unlock orders of magnitude and efficiency gains. So even if you just double your throughput in a certain factory, what it could allow you to do is make it efficient enough to not order it from abroad, which would allow you then to save on the shipping and allowing you to do a more lean process in which raw materials are directly turned into products and shipped to the consumer. I think the technology and external drivers are in place. We have global warming. We do have COVID-19, which has changed how manufacturers think about workforce and supply chain issues. And we do have tariff wars, which make it more attractive to do things in a more localized manner. The question is, what is the research that we should do? And so I would like to close with 3 ideas on where I want to go with my research. So the first one is, I think we have to resuscitate classic AI expert systems and planning and semantic reasoning. If you think about learning to woodwork, you would get a book about woodworking, and you would maybe watch videos about woodworking, and then you would eventually start trying it yourself and do some experiential learning. Right now, learning is fully focused on experiential from scratch learning. Instead, I think we should use deep learning to ground rules and deep reinforcement learning to ground controls. But we need new learning paradigms to deal with discrete representations and blend them with those continuous ones. We also need to do more work in human-robot collaboration to represent tasks. If I assemble an IKEA shelf like this to the right, by the way, again, a discrete representation is already there, so I don't need to learn how to assemble this. I can see it here. But if I have a robot sitting next to me, the robot wouldn't know really what to do when I say, hey, help me assemble that shelf. So there is some kind of programming aspect, but there's also some kind of reasoning aspect that humans and robots need to improve on. Finally, the grippers that I showed you are very, very good. We grasp very small screws and we grasp very big objects. We grasp strawberries and we assemble things, but yet there are certain things they cannot do. For example, at one of the manipulation competitions, the task was to use scissors to cut something, and scissors have nonlinear kinematics that the hand needs to adapt on. The only hand that could do that is the Pisa hand. It's now a commercial product. QB Robotics sells it. And I think we need to look more into hands like this in order to do all the tasks that a robot should do. What we also cannot do is in-hand manipulation. So here, soft robotics is very promising technology to do a large variety of in-hand manipulation tasks, which we will eventually need to do general manipulation. With that, I would like to thank all my students and co-workers at the university and at Robotic Materials. I'd also like to acknowledge the NSF, NASA, and NIST who have supported us with SBIR grants, and I'm happy to answer your questions via email. Thank you very much.